just about starting time anyway. So I did, as you'll note, a couple of things. Let me get back. And I just loaded this on Blackboard, particularly the PowerPoint we're really going to spend a lot of time on. Surely for us, at least over the next 2 sessions, possibly even as many as 3 sessions, one PowerPoint sequence starting with this 9A. And that's the one I just sent you. So if you look here in messages, I just sent this to you. It's rather lengthy. And it's got some great animations, one of which we'll look at today, about how muscles work. That's first on a hit parade. As we go from there, again, and this is, I don't know if you have access to the grades yet. They were due today. But please, you should avail yourself. Center for Student Success, and I contacted them last week, assures me they have tutors. Now, what their availability is, how that dovetails with your schedule. Please, even though that first exam you have the ability to drop if you choose to, and unfortunately, not just this class, a lot of students are going to have to avail themselves of that. Please think about that, because the next exam is a week coming up, and now that's really significant, and the material only gets harder. So I send that to you. This is the review recording. I try to make sure you guys got it early. So effectively, I'm getting in there 9 or 10 days in advance. Start listening to it. Again, I look right at the test. I just try to make sure I cover all the bases when I'm talking about it. And then I make sure the study guide, because I thought I had sent it. Apparently, it did not go. I called it a resend. I don't know where it went to, but when you're doing the technology, and this was the video from last time. So I'm going to pick up. That was from, obviously from another section. But that I really covered arthritis in that. I think that's significant, with the exception of where we're going to start today, which is this, the last 2 arthritides, form of arthritises, and only one of them is relevant on the test, and I think there's 1 or 2 question stops. And that's gout. That's coming up. Then we get it, and I'll talk about, I got to tell you a little bit about Lyme disease going forward, and then we'll get into muscles, fast and furious, and there's a lot. It's tremendously large amount of content in this particular thing, and it's absolutely essential to what we're doing going forward, because after we leave this, we go into the nervous system. That's our concluding. I try to make muscles almost a standalone for the 3rd exam, so I'm limiting the amount of content to basically a very large chapter. That underscores how important it is, and it should make studying for the 3rd exam a little easier than the others. So end the information portion of the program. So let's begin. So that's the one I just sent you. You can look at it. You can follow along with me. You can listen as we look at this. And I particularly find the animations very good. But I do have to finish this last one first, and we will get that done. Hopefully, we won't have noise accompanying us from outside, but you never can tell. Gout or gouty arthritis is, in arthritis, I talked about the most common kind, wear and tear. It's called osteoarthritis. He gets grandmas and grandpas my age, we all got something. It's almost impossible to avoid. Wear and tear, depends on your occupation, stuff like that. And I commented on it and I described it because I have a great deal of experience, not only from a personal aspect, but from treating people with this. So please listen to that information. I tried to pick out the best of my talks to the other classes doing the same content. And I talked about rheumatoid arthritis, which is sort of the poster child for what we call a true inflammatory arthritis. True inflammatory arthritis are typically what we call autoimmune. You'll learn about autoimmune diseases in AP2. Short course, your immune system attacks you. It's miscoded. It's white blood cells, antibodies, some byproduct of the immune system goes nuts and hurts you in the process. That's what an autoimmune phenomenon is. Down the road, when you start learning about diabetes in AP2, we think type 1 diabetes is most likely autoimmune in nature. Exactly what it came from, was it a virus? There's a lot of conjecture about that. So look at those, because I focus on the exam And the distinctions between those is on there, and it's on the review session, I promise. The gout. The gout is an oddball. The gout is a metabolic disease. Actually, you study it when you study diabetes, and you should. The gout is because we make a substance, make is the wrong word, we have a substance in our bloodstream all the time called uric acid. We're constantly breaking down and rebuilding cells all the time. The nuclear material in the cell, one of the byproducts of breaking it down and building it up, is something called uric acid. Uric acid, we can tolerate a certain amount in our bloodstream. It's the responsibility of our kidneys to get rid of as much of the uric acid as possible. Kidneys do that with a lot. It's got nitrogen in, and nitrogen wastes are an inherent problem to our bodies. So the uric acid is there. What happens when there's too much of it, it forms crystals. The analogy is if you have a pot of water and you add salt to it, it'll dissolve. When you get to the point where you have put too much salt in it, the salt starts to lay on the bottom. Effectively, that's what happens. The crystals start to show up in the solution. Don't dissolve. You reach a saturation point. In gout, those crystals aren't like soil crystals, which are nice little squares. Gout crystals are like little daggers. And they settle in joints and they irritate the joints, like sticking a needle into the joints. White blood cells come along, try to gobble them up. Can't, they're too big. And what happens is the white blood cells spill out, they burst and spill out all of these nasty enzymes that just make it worse. It's like a vicious cycle. It's hot, it's inflammatory. They've been dealing with this thing since they were in Egyptian hieroglyphs. Usually happens in the foot, sometimes the elbow, but most of the time in the foot. Between ages 35 and 55, it's a lot more common in men. After about age 55, men and women even out. And understand, not only is it to damage the joint from all this inflammation, if it's not treated, it can kill you, because these deposits will start settling in the heart, in the kidneys, in blood vessels. So it's not as innocent, oh, it's just a bad kind of arthritis. So that's the big deal with this. Uric acid and the crystals are very, very sharp and irritate the joints. And really, it's comparatively easy to treat. Years ago, they thought it was all about diet. Diet's a contributing factor. The current belief, it's been around for a long time, is that there's maybe a genetic fault or an inability to make a certain enzyme to keep those levels down, basically is what it is. And so it's kind of like blood pressure medicine. We have blood pressure medicine to kind of take care of the problem. As long as you can do the other smart stuff, eat ridiculously, smoke, drink. The same thing with gout. As long as your lifestyle is compatible, the medicines keep it under control. Very little side effects. So that's the saga on gout. You may get more in AP2. The last one, for the sake of completeness, and around here, you got to be complete with this. This is the number one. We'll get to this in micro, and I reiterate this, if you're going to end up with me for micro. This is the number one, what's called vector-borne disease. A vector means some other animal, and insects are part of the animal kingdom. So it can be an insect, it could be a dog bite giving you rabies, hopefully not, or an animal bite in the wild giving you rabies. That's a vector-borne disease. Most of the ones we deal with are like mosquitoes, like malaria. And the number one in the United States is this, it's a tick bite. And that's what Lyme disease is. There's a lot of areas where there's a lot of Lyme disease infected ticks because they're typically associated with deer. That's why we see it a lot in abundance in certain areas, particularly where there's an abundance of deer. That's part of their life cycle. I get into all of the ins and outs about that and why it's so relevant when we talk about micro, but we don't need to talk about that. There's no question on Lyme disease on this test. The question is going to be about gout. Just complete this. That's there. And the reason it's now categorized as an immune disorder, and it's now an immunological, it's kind of like it's kind of like the rheumatoid arthritis, but not, because Lyme disease is caused by a bacteria. So it's actually a bacterial infection, but what happens, initially you get a rash. Once the rash goes away, then it triggers your immune system and it very often affects nerves and joints, sometimes permanently, sometimes fatally. It can affect other organs. So it's not innocent. As long as it's recognized early, it's treated very successfully with antibiotics if you get to it early. The later you get to it, the longer the course. If you get to it when it starts to affect nerves and muscles and joints, then you're probably looking at a year of antibiotics. My wife had it, I think it was during the COVID lockdown when we were all off over that summer of 2020. But it was a classic presentation. Has a rash, looks like a bullseye. We call it a target shape. It looks like a bullseye target. And she showed it was on her upper thigh, which is where it frequently is, upper arms, upper thigh. And went over to urgent care. I can't even go in there with her because it was all the COVID stuff. And boom, about 3 weeks of antibiotics, good shape, no problems ever since. So that's the rest of the joints. So now that's done, when we can get to the, I hate to say it, the hard stuff. I had this talk with every other class, so I can't, I would be remiss not to include you. The exam that I did the dictation for, the review recording, it's mostly about bones and fractures and arthritis and some cell stuff. That material, I think, is just a matter of studying it. This material is more of a matter of trying to understand. And the way I framed it for the other classes, this is a lot of complicated material and a lot of terminology. Why do you folks have to know it? I mean, probably those going to physical or occupational therapy, okay, there's a good reason. A lot of what we're tasked with in any university, in any college, and again, it's part of the accreditation process, we have certain things we have to include in anatomy and physiology. Understanding muscle physiology is very significant. It's very complicated, and part of the test of going into fields, particularly when it involves people, is to be able to assimilate complex information, have a degree of understanding, and be able to answer questions reasonably to what we would call a passing standard, or higher than passing standard. That's part of what we got to do. No one is ever going to ask you about things like, how is this affecting my tropomyosin? Are my actin filaments in danger? You're going to see these terms. I'm throwing them out there. No one's ever going to ask this stuff. No one ever asked me this stuff. You know, I was operating on for this. Nobody. It's part of the process. Just something. So, I mean, it's more of a test of, it's something that you'll find useful, particularly because the course material, every time you go to a level, this is a 100 level, 200, 300, each of those levels inherently is more difficult. Micro is a 200 level course. Where in here, this goes to 2000 level, it's tougher. So I try to be completely honest with you and transparent about this. I got to. You know, I know it's difficult now that labs has gone by the wayside. It's time to concentrate on this stuff from an A&P perspective. I don't want to give short shift to your other courses, but you understand what I'm saying. Voila. Muscles. Half of your weight, typically, maybe more, depending if you work out a great deal, muscles. They're pure protein. It's just what they are. And a ton of it. Okay? Bones, we think are heavy. Comparatively, they are not. I mean, as they get older, yeah, I mean, I understand there's a certain amount of maybe weight change, but muscles are there. And they have the unique ability, and that's part of what we're going to look at today, is this ability to change chemical energy, ATP, that creates a particular kind of a signal, to mechanical energy. We're going to see an animation on this probably after a break called excitation, contraction, coupling. We're going to see it once now just for context. We'll see it next week probably as we really delve deeply. I'm doing that because there's so much darn terminology here. I mean, it's listen as closely as you can, please. And this is another issue. Again, if I say it to the other class, I gotta say it to all of you, all the classes. I do these recordings. It's your call whether you want to listen to them. Not a lot of people are listening to them. Coincidentally, not a lot of people did great on that first exam. Just saying. Do yourself a favor. Listen, start listening now if you're going to listen. So half the body's mass, transform that energy into mechanical energy and exerts force. We have to look at a bit of what the muscles are like. When they say muscle tissue, this is where we look at it on a microscopic basis. It's not lab playing name that muscle, okay, or what it's attached to or what it does. We're not going to sit here and go pectoralis major, biceps brachii, deltoid, trapezius, not sternocleidomastoid, no. We may talk about some of those muscles in the context of trying to make a point. In physiology, we classify them a bit differently. Some muscles are postural, some muscles are used for strength, some muscles are used for power. There's all sorts of different ways. Some we use all the time, like blinking our eyes and talking. Those muscles get used extensively because that's how we interact, to the most part, with the world, finger muscles. So there's ways of categorizing them. I talk about that. To me, it's not a big deal. Okay, so that's the type of muscle tissue, well, how it's made of and how it works. And our focus point by far and away, and this is skeletal muscle. Cardiac muscle is something, really, you dedicate the heart unit in AP2 to the heart. That's cardiac muscle, the anatomy and physiology. I'll talk about it in passing, maybe a few little nuggets about it, not a focus point. The big point here is skeletal muscle, the muscles we control, and a little bit about smooth muscles, which are muscles we don't control, just like the heart. Smooth muscles involve what are called hollow tubes, blood vessels, genitourinary tubes, ureters, oviducts, ductus deferens, all these in male and female reproductive or in and the urinary system. Hollow tubes. Blood vessels, I said. Bronchial tubes, hollow tubes. They all have muscle tissue called smooth muscle. And digestive probably as much as any. And then we'll look at the functions to a certain extent. Terminology-wise, these are the more common terms that are used. It's been a phone call-a-thon today. I'm trying to avoid them. You'll see we use all those terms. These are prefixes that imply muscle. Myo is pretty self-explanatory. Mist, you're going to see, also is used. Sarco is interesting. We're going to get to the unit that makes muscle work, skeletal muscle. It's called a sarcomere. So when we get to that level, we're microscopic, and that's really where our focus point is going to be. So most cells have cytoplasm. We call it sarcoplasm. Most cells have a plasma or cell membrane. We call it in muscle a sarcolemma. And the cell itself is different. It's an unusual cell. It's something you're going to be completely unfamiliar with because it's a multicellular structure that doesn't look like any other cell you've ever seen before. So the term sarco is for that. We talk a lot about the endoplasmic reticulum because calcium is stored there. That's called the sarcoplasmic reticulum. You kind of get the idea. And the unit, just like we talked about polymers and monomers, the unit, and this is really a repetitive thing, to coin a phrase, in all of physiology, this little unit called the sarcomere, we understand how this works, and you're going to just magnify it. There are thousands of them in muscle. They're tiny. We're even going to look at it even on a submicroscopic level, very, very small. And that happens in a lot of systems are like that. The kidney, you have 1 million in each kidney of what are called nephrons. If you basically understand how one works, you pretty much understand how they all work. So a lot of what happens physiologically inside the body is understanding one, and it just keeps repeating. So these are the types of muscle that are there. Skeletal. Skeletal muscle is voluntary. You and I control it. If I'm going to grab something, I've just decided to grab something. That's skeletal. That means voluntary. Skeletal muscle also has visible striations, stripes. We can see these particularly under the microscope. The striations we're going to look at today quite a bit. It has to do with what's called a banding pattern. And those stripes, normally when we see things that have visible stripes like that, the implication is power. Skeletal muscle is under our control and very, very powerful. The flip side of that, our cardiac and smooth muscles, we call them involuntary. We have no, quote, conscious control over them. Could we control them, and do we control them with medications? Sure. Could somebody who's adept at it and has a lot of experience, could they control it with meditation? Probably. You could lower your heart rate with meditation. You could probably meditate in such a way as to probably not to go to the bathroom for quite a while, I suspect. I mean, it's not something one does commonly, so it's much, much more the exception than any kind of a rule. But involuntary is just that we don't have conscious control over it, other than very extraordinary circumstances. But yeah, how most of the medicines we use happen to work on those systems. The medicines we prescribe work on those systems. Cardiac muscle has visible stripes microscopically. Smooth does not. It has stripes, they're just not visible. Okay, and that's where it gets the name smooth. It's kind of erroneous because the early anatomists didn't see it, so they called it smooth because they didn't see the visible striations with the technology they had. I'm just giving you the background information about that. The interesting one is cardiac. The stripes that are there, okay, are all about power. But these involuntary muscles are all about endurance. They just keep going and going. They're going constantly. All of you right now, the smooth muscles in your alimentary canal, your digestive tract are working very, very busy. Your blood vessels continue to work. The genital urinary system continues to work. You're all still breathing, it appears. All those systems are working. Okay? You don't even have to notice them. The heart is the ultimate mix of endurance and power. It's a very powerful muscle. It circulates your blood all over the body. And talk about endurance, it wins. Your heart beats more rapidly than once a second every second that you are alive. Thank goodness. Because if it doesn't, the flip side is true. You're no longer with us. We don't want to wish that on anybody. So only skeletal and smooth muscle cells are elongated, and the cell has a special name. This is where it starts to get confusing. We call muscle cells fibers. I know fibers have a lot. We talked about connective tissue fibers, collagen fibers, elastin fibers, blah, blah, blah. You have more terminology here. Those are true fibrous protein structures. When we talk about a muscle fiber, that's the actual cell. It has flexible rods inside of it. This is going to confuse you because it confuses everybody, myself included over the years, are called fibrils. So fiber is bigger, fibril is smaller. It's all packed with protein and they're all very flexible. You'll see it in a second. We're not done yet. When you get inside the fibril, it's filled with, you guessed it, filaments. So you have fibers, fibrils, and filaments. Why am I making a big deal out of that? That's what I think a lot of students have trouble with at this level. Is when they look at a test question, they don't read it thoroughly enough. I'm not saying that you're not trying to read it, but I mean, that's when I took tests, I would sit there and I would, I'd have whatever. So typically there were bubble sheets like you have, pencil, and I'd underline the question words, what I felt were the key words. So I would, if it was fiber, I'd have that underside. If it was filament, I'd have that underlined. I mean, I look for the key. That's really important because that is all about the questions, and then go find the answer. Students kind of read the question and start looking, and they start going one by one to the answer. It's bad technique. Because particularly when there's a time limit on tests, you get stuck. Rather than, I read the question, I know what the answer is, go find it, move on to the next question. All right. You have to use all these little methods. I'm not, despite what people try to tell me, I am not that smart. I am a great tester. Always have been. It's a gift. So I'm the world's worst athlete. You get lucky on some stuff, but not others. So skeletal muscle tissue, skeletal muscles attached to bone and skin. Here's the stripes. Here's the voluntary conscious controls. And this is very true. They contract rapidly. They tire easily. You'll see when we get to the latter parts of the chapter and we start looking at energy utilization, there's a way, and that's where really when you hear about aerobic exercise, when you're on the treadmill in the gym and you can stay on there for a long period of time, okay, you've converted to something called aerobic activity. That's what my soon-to-be 43-year-old eldest is going to do, running around Washington, D.C., doing like his 6th or 7th marathon. He's doing the Marine Corps marathon. There's no explanation. Apologies to anybody who likes to do those long runs things. Why would you run 26 miles to get back to the same place? Uber? So that's very true. So the key word, skeletal, striated, involuntary. Cardiac, only in the heart. That's why we're not really doing it because of its location. The heart is a giant muscle. I don't know if you do them in AP2 when you dissect the sheep heart. I happen to have cows' hearts, and it's unbelievably large, and it's ridiculously heavy. It's just a giant muscle. Striped, striated, involuntary. And so this is what happens. It's the rate. I don't want to get into all this about the controls, but let's say that we have things that impact their controls. And so cardiac, striated, involuntary, and smooth, hollow organs, and that means all these tubes, stomach, nothing more than a tube, just expanded. Bladder, part of a tube, expanded. Airways, not striated, not visibly, involuntary. Visceral means organs, the internal viscera. All that stuff in the thoracic, abdominal, and pelvic cavities. So another way that we refer to them collectively is your viscera. And you'll see that at the very end of the course, we talk about the autonomic nervous system, and the word viscera is used a lot. And this is just some of the micrographs. So I'm not going to ask you anything. That's lab. That's there. This is a big deal. One of the things that's on the exam you're taking next week is excitability. Okay. Basically, you're talking about resting membrane potential. Every cell has a resting membrane potential. Nerve and muscle cells have excitability. What that means is that at a signal, whatever it is, a chemical signal, a physical signal, whatever triggers it, it basically along that membrane can rapidly send a signal. Remember, it's positive on the outside, negative on the inside. It flip-flops it. Bang, 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 bang. And it's, again, ripples in the water, throw a rock in the water, any analogy that works. You're putting a sheet on a bed and you kind of flip it like that, and you can see how it kind of ripples a little bit. That's basically what excitability is of a nerve. That membrane is rapidly, for lack of a better way to express it, flip-flopping from positive to negative, and then negative to positive, and it rapidly flips. And that change creates a current, electrical energy that flows across it and will eventually trigger things wherever it's going. So that's excitability, the ability to receive and then to respond to stimuli. And what is unique, the word shorten is very important. When muscle contracts, it doesn't bend. We're going to look a little bit today to show you something called the sliding filament theory. What that is you're going to see these filaments slide over one another. Actually, they're not getting shorter, they're not folding, they're not bending, they're not twirling or anything like that. Basically what they're doing is kind of going one over the other. And in doing so, they shorten the unit they're in, that you're going to see, called the sarcomere. And we add that. So effectively, when the muscle fires, it shortens. But depending on how the muscle is arranged, we often see it differently. The biceps brachii. I know you did this with Dr. Robbins. Okay, he went over the shapes of muscles: unipennate, multipennate, convergent, right? Parallel or strap-like, fusiform. Biceps brachii is a fusiform muscle. Fancy word to mean it's narrow at the ends and wide at the belly. So when all these things shorten, we get the illusion of this thing like folding up and like coming together like that. So you see that big muscle when somebody works out has those. Side note, not me. So it's based on the shape of the muscle, but that's how we know the muscle is moving. So I may be bending the part, but I'm doing this because that muscle is effectively shortening. The bulge is secondary based on the shape. So, and then you'll see that there's special proteins. You're going to see the name of it when we get to it, called titin, Titin. And that it's shaped like a spring. So it looks like a spring or a coil. And effectively, that's something that allows for this extensibility. It can stretch. And when it's stretched a little bit like a spring, it pulls back. So you'll actually see this in a particular protein. Again, proteins are about shape more than anything else. Shape kind of determines how they move. You're going to see the two proteins that make the muscle slide over one another. One is called actin, something you've heard about before. The other one is new. It's called myosin. Myosin is a true motor protein. It changes shape and it provides means for movement. That's one of the ways the filaments slide over one another. You're going to see that a little bit today. So that's all the kind of stuff. And so, I mean, here in this, the 20 minutes I've been telling you about this stuff, 15, 20, it's a whole lot of terminology, a whole lot of stuff. It's complex. I'll buy that. This is my heart-to-heart day with the students to try to let you know the intensity is going up because that's the nature of the subject material. To me, these are the hardest units. This may be the single hardest unit that you have in AP1. And then because the next unit, when we talk about how nerves work and the nervous system, we've already covered a lot of it here. We just reinforce it there. And I think a lot of the systems when you get into AP2 are a little more straightforward. There'll be some hard ones, but a little more straightforward. Okay, so muscles, they move, make things move, we know that. Walking, again, pumping blood around, digesting, posture and body position, I'll buy that. Sure, it stabilizes some joints, generates heat as they contract when you shiver. Like this room's cold. The room, if you're in the room next door today, oh my goodness, it's 95 degrees. Don't worry about it. They'll have the air conditioning on in the middle of winter here. The advice I give to everybody, I see many of you are following it, dress in layers around here. You never know what temperatures. My colleague was telling me about hail. Like it's just, you could get any temperature in there. I play the age card, tell them I can't make it over here. It's okay. I'm decrepit. So skeletal muscle, an organ made up, nerve, connective tissue, sheaths, and attachments. More anatomy. And I don't know that you covered this. I give it a very, very limited amount of time because you may have gone over this. Did you do any of this stuff with Dr. Robbins? Is this ringing any recollection bells? Yes, no? Yeah, a little bit, I would think. So we control it. Nerves, arteries, and veins come from the outside. You're going to see that the blood supply in a nerve, when we start looking at nerves, is already is in the middle of the nerve rather than coming from the outside. But we'll get to that. So they're similar but different anatomically. And oh boy, oxygen everywhere. And oh boy, a lot of waste products. When we use our muscles, think of an activity you do. You do something vigorously outside, inside, whatever you're doing. I mean, and shoveling snow outside is a perfect example. You fatigue very quickly. Okay, you have to stop, and that's when we talk about stop and catching our breath. We'll go over why we have to do that. Okay? And they have a fancy name associated with it, and who cares? But the thing that a lot of people notice is the muscle starts to hurt, I'm feeling pain. Those are waste products. The things that make your muscles spasm is sort of the that's right. You can see cramping up on the sidelines in every game. Every football game they're out there. Oh, it looks like a cramp, and they're stretching it out. Those are waste products. When you're something that is that active and using a ton of oxygen produces a ton of waste products, you have to have at least a certain amount of time to get rid of them. The difference with aerobic exercise, a la distance running at pace, is you're varying your breathing and the amount of movement in your blood supply in an effort to get rid of all of those things and be able to continue for hours at a time, which is even somebody out of shape can do it. Like when I go on the treadmill, I can do 2-3 miles, even with a modest pace and at elevation. This usually happens when my wife has yelled at me sufficiently to get my rear end over there. So I was going to say something else, didn't you? So, connective tissue. There's 3 sheaths. Go for me to get that one out. Sheaths. Okay, wrappings. Same in nerve. They even have similar names in nerve. You're going to see the terms. Here, that MYS. The whole muscle is wrapped in a dense connective tissue. Like anything else. We don't have the luxury. We had a cadaver to look at. That thigh, giant muscles. All of those muscles are sort of individually packaged. They have this dense connective tissue around them. And then moreover, they're bound to the bone in the thigh and in the leg and the forearm and the arm by something called fascia. The epimysium is really a combination of that. It's very dense, it's very, very thick, firm. It really holds everything together and helps hold it against the bone. That increases mechanical advantage. The peri means around. You're going to see little bundles are inside, because when we look at the muscle, we don't look at the whole length of it like that fusiform or strap leg or conversion like pectoralis major. We look at the cross section, as you will see shortly, and they're in bundles. Each of those bundles are called fascicles, and they're surrounded by something called perimysium, which is not nearly as thick, has a lot of fatty tissue in it. And further still, each of those fascicles, as you will see in a second, the individual cells are surrounded by something that's very fatty as well, called endomysium. That surrounds the individual fibers. Fiber and cell, when you talk about muscle, are interchangeable terms. Fiber can be, an individual muscle cell can be 8 foot long. Individual nerve cells, I think cells are the wrong term. Individual nerves, better term, can be 1 meter long. The longest, if you probably had this in lab, I would have had it. I say some of the other students, there's a muscle that goes from your hip down to below your knee. That's the longest muscle. It's called the sartorius. You might remember that. That's one of those strap-like parallel muscles. Very neat muscle. Here it is. So imagine, here we're looking at probably hamstring. So if you see, it's the cooking thing in me. You ever watched a show where they showed you how to make ham? Okay, basically, that's the ham, that rear part of the pig. They basically take the hamstring. Another way we get the name ham from hamstring, or the other way around, one way or the other. And basically, they take that whole thing off, and you basically salt it and hang it. Okay, and now whether you cook it or not, that's different. And so they make a wonderful culinary delight called prosciutto. So if you're, I'm a foodie, so they have different types, but that's basically how those hams are made. So I don't know which came first, the name of the ham or the name of the hamstring, but we call these hamstrings. So you can see this, and you imagine you're slicing it. So you go to the grocery store, you go to where the meats are, I mean, you can go where they'll get them for you, and you can pick your own, where they have them already laid out. You're looking at cross sections, and those different cross sections will tell you whether it's a sirloin, whether it's a round steak, whether it's a T-bone, whether it's a porterhouse, et cetera, et cetera, et cetera. And that's what this is. So the outside, that epimysium is very tough. You can't really eat it. This is a fascicle. Each one of these dividers that are quite large and distinctive are a fascicle. When we look at these things, you see the fat around it, and the fat inside it is something that in the culinary world we call marbling. So when you go into the grocery store and you see how expensive typical meat is, which is choice, and you see prime is a lot more expensive because it has more of this pattern in it. It depends what your budget affords. And so here we pull out one of those fascicles. This is in the fascicle. The fascicle are bundles of fibers. Those are the cells. And you can see what's in the fibers. More flexible protein drops. It's just, all of it is just chock full of protein. There's not a whole lot else in muscle. There's some membrane tissue, there's some blood vessels, and other than that, protein. There's mitochondria. There's some other proteins that carry oxygen, other things that store energy. And other than that, muscle. It's nearly as close to pure muscle as any tissue in the body. So here's that muscle fiber, and look, you're going to see it's unique because it's a cell that's developed so much so that it has multiple nuclei. So this is it's almost a confluence of cells that have developed over time. You're born with all of them. You can't make any more. They are amitotic. They're out of the cell cycle. So if they're damaged, you're going to heal with scar tissue. So when you hear somebody about tearing a muscle, for most of us, it'll get better and it'll heal. It won't impact us. We can rehab it. We'll probably be able to do the sports we do or the activities or whatever we do easily. Only at people at the high end. You know, you're talking about interscholastic athletes here, serious amateur athletes. Yeah. And the damage is worse the more elite it is. Professional athlete and Olympic athlete, a little damage is the difference between gold medal or a championship versus, for us, for you and I, probably not a big deal. So understand that's why this is a unique tissue. You can't make any more of it. So what is that individual cell with? More flexible rods of protein. As you'll see when we pull them out, I'll show it over here. Now we're getting into, I'll come back to all of this. Now we're into what are called fibrils. So here's that cell blown up. Here you can see the stripe pattern. Here you can see multiple nuclei. And it's filled with, requires a ton of energy, so there's a lot of mitochondria. And you're going to see it has a lot of nutritional source that we store there just for those muscles to work, because you never know when you're going to need them. And we require a lot of oxygen. We have an oxygen source. So I wanted to give you an idea. This is where it's headed. It's all these repeat patterns. And what we're going to head to today, probably before we grab a quick break, is to start to just at least identify this, which is called the sarcomere. Between those blue lines, that's the repeat pattern. They're like little boxcars. That's where the fibers slide over one another. And as they slide, effectively they shorten. It's like a little cylindrical house. It's like being in this room, and magically we can pull the walls closer together. And we shrink the room in that direction, shortening it. We're shortening it from the windows to the front. Doesn't matter which way we go. And effectively, by shortening that, keeping the insides the same, but just allowing the filaments rather, to slide over one another, that accumulation of motion with these thousands of these individual repeat units you'll come to know are called sarcomeres. That's how muscles work. So let's go back to the anatomy portion of the program. I know you're waiting intently. So this is what it looks like. I don't know what cut of meat that is, but it looks hard to digest. So what do we do with that? That's what stuff you grind up. Yeah. Food moment. So this is lab origins and insertions. I call them attachments. I think it's a better way to describe them. And yeah, some of them go directly into the bone, some of them indirectly by tendons, or they insert into what's called an aponeurosis. It's again, that's like that. Here you have a thing called the ligamentum nuchae. The rectus femoris, your six pack. What makes it so distinctive? Your six pack, not mine. My six pack is probably Yingling Flight. Okay, Michelob Ultra. Not that you guys would none of you would know about this. Oh, but did I mention any? I told you some anecdotes about my daughter. Remember I told you the one about going. Remember I didn't tell you that? Sure I did. See, when she was 19, the brothers are 21 and 22. I thought I told you. And then right after Thanksgiving dinner, they typically would go and line up at the stores for Black Friday. In the meantime, oh, where we're going? We're going to Southside. Remember I told you that? Yeah. Oh, but you're underage. Oh, don't worry, Dad. I'm not going to. You're not going to drink? No, I got a fake ID. Only arrested once. Don't laugh. Could be you. You're a good girl. I understand. It's okay. My daughter's. I love her to death, but she was a trial. So, effectively, the aponeurosis is some of this kind of tissue that we see. So that's called the linea alba, where the six pack is. It just looks that way. It's totally opposite of me. She doesn't do it anymore, but for Washington fitness modeling, it goes gets up at 5:30 and works out. I get up at 5:30. I'm ready to eat. So here you are, epimysium on the outside, fascicles come out. The fascicle, pull that out. Now you have a fiber, the cell. Let's look at the fiber. You see the striations. So that's what's meant. They alternate light and dark. We're going to get to why they are light and dark. They have lots of nuclei. They have lots of mitochondria. The outer sleeve is called the endomysium. Epimysium here, perimysium around the fascicles, endomysium, and you can see what's under the sarcolemma. Again, that fatty lining is the endomysium. Underneath it is the cell membrane, except it's got a fancy name. Sorry, it's the name. It's called the sarcolemma. Sarco means we're down at the individual muscle fiber or cell level. And then we pull out all of those flexible rods, which are identical, okay, are called fibrils. And it just gets worse. When you open up one of those fibrils and you look at that banding pattern I was showing you, that's where you get to the filaments. Aren't you excited? You see or not? I don't blame you. So skeletal muscle fibers are long and cylindrical, multinucleated. That's why you can't replace them. The actual membrane is called the sarcolemma. The cytoplasm is called sarcoplasm. I didn't make it up. They named it. Glycosomes, the way muscles' energy storage comes from a chemical called glycogen. It's one of the ways we store sugars. Very limited. 2 places. Skeletal muscle and your liver. It's kind of like your emergency supply. We replenish it. So you go out and, like my wife said, take out the garbage. Come back in, you use a certain amount of muscle. As soon as you stop, they replenish the glycogen that's in them. The other thing that gives it its color is called myoglobin. What gives your blood color, you study in AP2, that is hemoglobin. So you have, they're very similar. They both have iron. That's what gives it a reddish color. The difference between red meat and white meat, like if you're looking at, if you're having turkey for Thanksgiving, as most of us are, the breast meat is white. It's not used a lot, so it doesn't have a lot of myoglobin. The turkey runs around in its legs, walks. Turkeys don't run. We have wild turkeys crossing the road. Like you could honk forever, and they're just kind of like. My wife and I look at each other and go, "That's why they call them turkeys." It's a perfect name for them. But understand that's the difference between usage is the difference between red meat and white meat. Technically, all of our meat is red. It just depends how much we use. And so inside the organelles are modified. The organelle is actually these packets of proteins that are flexible. The sarcoplasmic reticulum is a unique bit of reticulum. And the T tubules we will get to very shortly. So I don't want to put the cart before the horse. The myofibrils, flexible rods, thousands, and it's all these repeat units. So imagine if you have a teeny tiny bit of motion, not emotion, but motion, of pulling the walls closer together and shortening, and you multiply that by thousands or 10,000, imagine how much motion that you could have proportionally. You'll see the striations shortly. You'll see the actual sarcomere, the repeat unit, and you'll see effectively how it moves, the molecular composition, how they filaments slide over one another. That's what we're going to look at. I left it here. And we'll stop it here. We'll take a break, and we'll do this next bit afterwards. Okay? So let's go give my voice at least, 10 minutes, 4 o'clock. Deal? So I'm going to